By the way, you might have noticed there's no Justin. Went to go stare at the sun or something. There's no Peyton, so I'm his secret, cooler twin brother, and I'm here to tell you all about Quicksort. So I hope you're ready. Okay, Quicksort is really cool. It's so cool that those other two clowns could not do it justice. So I'm here to show you coolest known sort. So I hope you're ready. So those other two weirdos, they came and they were like, oh, selection sort is n squared. I hope you're impressed. But you weren't. You wanted to see the fastest known empirical sort, which was none of these. It was the sort we will be seeing today. Those two guys, forget about them. They don't know about this. Okay, so far you've seen these sorts, and they might have told you, they might have not, that the way that you keep the sorts distinct in your mind is to remember that each of the sorts has a different core operation. For example, selection sort, the thing you were doing over and over again was take the small item, put it at the front. Insertion sort, the core operation was swapping items and traveling them forward. But quicksort, it's built on this much stranger, very cool core idea, which is the thing I want to show you. And so the weird thing about quicksort, to begin this story of coolness and weirdness, is that it was actually invented by this novice programmer called Tony Hoare. And Tony and I, we're pretty similar. We have the vision to see something like quicksort. And so what he was doing was he was running some sort of machine translation program, and he needed to sort a list of words. But this was 1960. There was no Google. So Tony, just like me, whenever I'm stuck on a problem, because I'm the cool version, I just invent the sorting algorithm myself. So that's what we'll be doing today. So here's the core operation that makes quicksort work. If you have this core operation, the rest of today is just putting the rest of the pieces together. Core operation is called partitioning. So to do a partition, the first thing you do is you pick one item. It's already kind of strange that you have to arbitrarily pick one item, but that's what you're going to do. So I pick one item. Here I chose 10. You could have chosen something else. And what I want you to do is I want you to rearrange the entire array. You can swap any items around that you want, including the 10. So you can move everything around. But the result should be such that everything to the left of 10 is less than or equal to 10, and everything to the right of 10 is greater than or equal to 10. That's the rule. There might be multiple valid partitions, but I want you to run an operation such that everything to the left of 10 is less than or equal to 10. Everything to the right of 10 is greater than or equal to 10. So now the question for you is, which of these partitions actually makes sense and obeys the rules that we just talked about? So you can try and guess, and remember, everything to the left of 10 has to be less than or equal to 10. Everything to the right of 10 has to be greater than or equal to 10. Does anyone see one that for sure doesn't work? D. I don't like D either, because look, here's 10, there's 4 to the right. That doesn't work, because everything to the right of 10 has to be greater than or equal to. And if you go through, you check them all, you'll realize that the other ones are OK. So there were 3 valid partitions here. There are more out there, but these are the 3 that we chose. By the way, just to bring it up, because since sometimes people ask, the 10 could move as part of the partition. So it does not have to stay in place. But the cool thing about partitioning, I guess before I go on, is that once everything to the left of 10 is less than 10, and everything to the right of 10 is greater than 10, if you look at this 10, it's in the right place. How do I know that? Because whatever the actual sort is, I don't know what the correct sorted version of the array is, but I know that everything less than 10 has to be to its left, everything greater than or equal to 10 has to be to its right. So therefore, this 10, it must be in the correct place. So somehow, by partitioning, I have actually sorted the array on one item. Kind of a weird idea, but that's what we'll be doing, because we're cool, and you don't want to tell those other two guys that we're doing this. But that's the idea. We're going to sort an array on exactly one item without regard to the others, and the way to sort an array on one item is to put all the items less than to the left, all the items greater than to the right, and you're done. That one item that you partitioned on is in the right place. We don't know where everything else goes, but the one item found its rightful place. So question for you then is, how do we actually partition? What is the algorithm for doing this? I showed you some answers, and you told me which ones were valid, but how would you actually do this? It turns out there is also a very cool algorithm to partition an array. But before I show that to you, let's think about what those other guys would have done, because those other guys, they're not like you and me. They don't have the vision to see these cool algorithms. So they probably would have done the dumbest thing they could think of, because that's the kind of guys they are. I know how they think. And so tell me, if you were those other guys, what's the simplest partition algorithm you can think of? So try and come up with something. It doesn't even have to be, asymptotically optimal. It doesn't have to be memory efficient. Just come up with the simplest thing you can think of, such that, and here I want to partition on 6. So I've chosen 6 to be my partition because I got to choose something. I want everything less than 6, which I've helpfully highlighted in red to show up on the left of 6. And I want everything that is greater than 6, or sorry, greater than or equal to 6 to show up on the right of 6. So I just need a valid partition on 6. Everything less than or equal to 6 on the left, everything greater than or equal to 6 on the right. There are multiple answers. Here are 2. So think like those other 2 people. Give me the simplest algorithm you can think of. Does anyone have one that they think like is just going to work, and you don't even have to draw me pictures to convince yourself that it works? Scan the array and do what? Scan it? Sorry? Sorry, say that one more time because I can't hear you. Take the 6 and do what with it? Oh, comparison, sure. And then what do you do once you finish comparing? So let's say I look at the 8, it's greater than 6. What do I do with it? I leave it in its place, and then what if it's less than 6? Put it to the left. Oh, so I'd have to swap it over? Yeah, that might work, right? I think if you do that, you actually end up doing insertion sort to some extent. So that would work. Yeah, you can maybe swap some elements around. There are actually tons of valid answers to this one. And we'll see one. We'll see more later. Oh, do you have batteries for me? OK. Hold that thought and maybe think about some other algorithms while I swap batteries real quick. Yeah, I think all those are dead. OK, just kidding. We're going to be using this mic for a little bit longer. All right. So there's all sorts of other algorithms you can think of. Here's one that I like, which I think just works. Where did the slide go? I don't know. I guess we're too cool for the slide. So one approach that I think works just fine is let's just scan all the elements and copy all the red items. So I scan, don't copy, don't copy. OK, I see the 3, I copy it. The 1, the 2, I don't copy this, and the 4. So I wrote those down. And then I go back to the beginning and I scan again and I copy all the white items. And then I look left to right, scan the array again, and I copy all the blue items. So hopefully we're convinced that that will work. Is it the coolest partition algorithm? No, because this is the ones those other guys came up with. But it will work because I just scan the array 3 times, copying the less than items first, copying the equal items first, and then copying the greater than items last. OK, that's going to be good enough for now. We will come back and come up with more clever partitioning algorithms later. But at least we know what a partition is, and we know how to compute it. Good. So with the core operation, we know that partitioning is the operation that's going to make Quicksort work. We can now apply this operation over and over to actually sort the array. Because after you partition an array, here I partitioned on 6, is this array sorted? No. 3, 1, 2, 4, that's not sorted. But if I partition some more, maybe I can get it sorted. So that's what I will do. So here, I'm going to pick any item to be the pivot. I will choose the leftmost for now. So I chose 5. I partitioned on 5. So now 5 is in its right place. And I know that this 5 is not going to move again because everything to this right is greater than or equal to 5. Everything to the left of right, or 5, is less than or equal to 5. So this 5 is in the right place it should be if the entire array sorted. So now we could maybe partition on some other elements like 3, 2, 1, 7. But if I look at this, okay, so that's the order that things got swapped according to my 3-scan partition algorithm, where I just copied all the less than items, then the equal to items, and the greater than items. So the question is, how would I use the partition algorithm or operation over and over again to actually sort this array? Well, one thing I could do, and I bet if those other guys were here, they would show you this, is maybe they would just take the next element, 3, and then partition the entire array on 3, find out where it goes, and then take the entire, take 2, partition it on the entire array, find out where it goes, and do this over and over again. But if you do that, you're kind of wasting some work, because if I look at this 5, it sort of acts like a wall, because think about all the things to the left of 5. 3, 2, 1, and 4. Could any of them cross over to the other side of 5? No, because they're all less than 5. And what about 7, 8, and 6? Could any of these cross over to the left of 5? No, because they're all greater than or equal to 5. So not only is 5 in its correct place, that is, when I finish sorting the array, I know that's where it's going to land, but I have actually formed 2 smaller subproblems. I no longer have to go back to this big problem to continue partitioning. I could actually just solve the small problem to the left and the small problem to the right, and once they're both solved, I will be done. That's the cool observation about partitioning, is that after you finish partitioning, not only do you find the correct location for the number 5, but you've also now created 2 smaller subproblems that you can solve separately. And once you finish solving each side, you will have a sorted array. OK, bask in the glory of Quicksort for a second while I swap batteries. Sorry. OK, thanks. Oh, those are the old ones. Thanks. OK. OK, hopefully it's still OK on Zoom. OK, so here you can see I now have 2 smaller arrays, the 3, 2, 1, 4, and the 7, 8, 6. I sort each side separately, and my array will be sorted. OK, good. So at this point, by the way, what you could do is you could say, I'm going to, I'll merge sort the left half, and I'll merge sort the right half. You could do that, but maybe to, I don't know, fully use Quicksort all the way to the end, what if I quicksorted the left half and I quicksorted the right half? So it's a recursive algorithm. So I could do that. If I wanted to quicksort the left half, I would take the number 3. It would be my new partition, because for now I'm just choosing the leftmost item as the partition. I would take all the items less than 3, put them on the left of 3. All the items greater than 3, put them on the right. Do I have to worry about 7, 8, 6? No, that's a separate subproblem. That's someone else's problem. And so I can partition on 3. This is a valid partition on 3. It's not the only one, but it's one of them. Everything less than or equal to 3 on the left, everything greater than or equal to 3 on the right. And likewise, on this side, I chose 7 to be the partition. I partitioned on 7. And now I've actually created 4 smaller subproblems. So you see where this is going. Now I have this subproblem, which is 2 and 1, this subproblem, which is the single element, this subproblem, and in fact, the 3, the 5, and the 7, the 3 things I've partitioned on, they've all fallen into their correct places. So when I finish sorting the array, I know that this is where the 3 is going to go, that's where the 5 is going, that's where the 7 is going. That's Quicksort. It's based on partitions. So you partition. For now, we'll choose the leftmost item. Later, show you, don't tell the other guys, but I'll show you something cooler. And then I'll quicksort the left half, and I'll quicksort the right half. So just to see it in action one more time, and then you can stop me for thoughts or questions. I will take the leftmost item, which is 32. And I've helpfully colored everything less than 32 red and everything greater than 32 blue. You don't have to, but I did on the slide. And I partition on 32. So everything to the left of 32 is less than or equal to 32. Everything to the right is greater than or equal to. You get the idea. Now I've created 2 subproblems. So I'll quicksort the left half, and I'll quicksort the right half. 32 is locked in place. I don't know what the true sort is yet, but I know whatever the true sort is going to be, that's where the 32 is going to go, for sure. Then I can quicksort the entire left half. Then I can quicksort the entire right half. So I kind of skipped over things, because that's the kind of guy I am. But if you were like those other 2 guys and you want to see it in more detail, there are some extra slides that will walk you through the entire thing front to back. So if you're not convinced that the recursive step works, check this out. You can watch the partitions go all the way down. And in fact, here's actually a recursive tree showing you what partition operations happen. So for example, the 32 was the first thing we partitioned. And then we had 2 subproblems. Remember, we partitioned the 15 and the 41. So there's the 15. And then the 15 partitions on 2 smaller problems, so forth. So that's Quicksort. You partition and partition again all the way down. And the 2 key ideas I want you to take away, one of them is how partitioning works, what the operation actually does. And the second key idea is that once you partition, you create 2 smaller problems. That's what makes Quicksort fast. It's the fact that after you partition, there are now 2 smaller subproblems that can each be solved separately. Kind of has the same flavor as merge sort, but it's a bit wilder. OK, so that's Quicksort. There are extra slides. What do you want to know about Quicksort before I show you more? Runtime, soon. How do you manage to find the middle point? Soon. Anything else? Okay, there were two good questions on Zoom, but they'll be answered in due time. Okay, so that's Quicksort. By the way, in terms of naming, if I were to name this using the same naming convention as the other sorts, I would have called it partition sort because that's the operation that it's doing, just like how we called merge sort because it was merging at every time step. But Tony and I, we're built different. So instead of saying partition sort, we just called it Quicksort, even though we didn't know it was the fastest sorting algorithm. But it turns out Tony was either lucky or had the vision because Quicksort is actually the fastest known sort. If you run experiments, it's fast. Okay, so the next thing we will do is try and calculate how fast exactly is the fastest known comparison sort. So that's coming up next. I saw someone predicted a runtime in chat earlier, so let's see if you're right. So let's start with the best case. Let's say we get super lucky, because not only am I a pretty cool guy, I'm pretty lucky too. So what if I'm very lucky and every time I choose the pivot, so I choose this item, turns out half the items are less than the pivot and half the items are greater than the pivot. So every time I choose the pivot, I get super lucky and it lands exactly in the middle because half the items are to its left and half the items are to its right. So I take this array, you can pretend it's got some numbers inside. Let's say I get super lucky and this item, it lands directly in the middle. All the items to the left are less than this item. All the items to the right are greater than this item. By the way, sometimes I say less than, I mean less than or equal to, so sorry if I tripped you up on that. Great. Now I have two smaller problems, so I'll solve each one separately. And let's say I get lucky again. This pivot that I choose for the left subarray happens to land in the middle. This pivot that I choose for the right subarray happens to land in the middle as well. Okay, great. Now I've created 4 subproblems. And for each subproblem, I choose the pivot. And let's say I get lucky again, and that pivot lands in the middle of its subarray, so that half the items are less than that pivot, half the items are greater than that pivot in that subarray. Okay, great. And now these are all the things left to be sorted in green. Everything in black has already been the pivot once and has already been sorted into its rightful place. All these are of size 1. So if I partition on size 1, I'm done. It's a base case, and so we're done. So that's what Quicksort looks like if you get lucky and every pivot that you choose lands directly in the middle. So what kind of runtime are we looking at here? Well, one thing we could do is, it seems like a recursive algorithm. So I want to draw that recursive tree and think about how much work is done per call and per layer and things like that. So let's see. Well, at the top level, how much time does it take to partition on this leftmost item? I guess I didn't tell you how long that silly partition algorithm from earlier, the 3-scan approach, took. But hopefully it doesn't feel too much of a leap that it takes n time, because I have to scan the array to find all the items less than the pivot. I scan the array again to find all the items equal to the pivot. And I scan it again to find all the items greater than the pivot. Each scan takes n time. There are 3 scans, still theta of n time. So at the top, I run approximately n work to create this pivot where I shuffle all the items around. Everything less than is to the left, everything greater than to the right. Now I have 2 smaller subproblems. How long does partitioning on each one take? Well, on this side, I have roughly n over 2 items, and I have to partition, so it's going to take me n over 2 time, because we know partitioning is a linear time. On the right side, I have n over 2 items. I need to partition on them, so that will take me n over 2 time. So there are 2 subproblems. Each one takes n over 2 time. So at this level, there's a total amount of n work. Maybe you see where this is going. At the next level, I now have 4 subproblems. And assuming perfect split, every time I choose the pivot, it lands in the middle, then I have 4 subproblems. Each one has n over 4 items. And there are 4 subproblems. So the total amount of work is n again. And again, and again, and again. So as I go all the way down, the amount of work done at every level is n. And how much smaller are the subproblems getting? Well, at the first level, the subproblem was size n. And then at the next level, the subproblems were of size n over 2, and then n over 4, n over 8, n over 16, all the way down to problems of size 1. So how many times do I have to divide n by 2 before I reach 1? That happens to be log n. That's what log n means. It's the number of times you cut n in half before it reaches 1. So there are log n levels before I can divide this problem all the way down to size 1 problems. And each level takes n work. So my total runtime is theta of n log n in the best case. Okay, great. Thoughts, questions? Is that okay? Kind of has a similar flavor to merge sort, but we did it with partitioning instead. What about the worst case? The worst case would be, what if the subproblems weren't so perfectly balanced? So right here, when I chose the pivot, it landed in the middle, and I got two subproblems that were perfectly balanced. But what if that wasn't the case? So what if I chose the pivot, and it actually stayed in place? It stayed on the leftmost side, and I created two subproblems. One of the subproblems is everything, and the other subproblem is nothing. In other words, whatever pivot this is, there are no items less than or equal to the pivot, and every item is greater than or equal to the pivot. They all end up on one side. Well, then I have to solve both subproblems. The left subproblem takes me no time to solve because it's nothing. The right subproblem has n minus 1 items. I have to solve that. What if I choose a pivot, the leftmost item, and I get unlucky again? I'm like, oh man, well now, again, if I choose this pivot and I'm unlucky, I still get two subproblems, but everything to the left of this pivot is nothing. That is, there are no items less than or equal to this pivot. All the items are greater than or equal to this pivot. So I get a problem of size n minus 2 that I have to solve. And then to solve that, if I get unlucky again, see where this is going? I choose the pivot, I'm unlucky, all the items end up to the right of the pivot. I have a subproblem of size n minus 3 to solve. So this creates a sum that I can compute, which is, well, here I have n work to partition. I create a subproblem of size n minus 1. To partition that, it takes me n minus 1 time. Creates a subproblem of n minus 2. I have to take n minus 2 time to solve that subproblem, n minus 3, n minus 4, all the way down to 1. What is the sum of n plus n minus 1 plus n minus 2, all the way down to 1? Well, that's theta of n squared. It's kind of weird. Even though Quicksort is the fastest known sort, it actually has a case where the runtime is n squared. By the way, if you're wondering, would I fill in these boxes to cause the worst case behavior? Like what numbers would go in these boxes for the worst case Quicksort? Here's a possible sequence of numbers. Try plugging this in, 1, 2, 3, 4, 5, 6, and you'll realize that if I partition on 1, everything ends up to the right of 1, and I get a subproblem of size n minus 1. And then if I choose 2 as the pivot, everything ends up to the right of 2. And then I choose 3 as the pivot, and everything ends up to the right of 3. And every single operation takes n minus 1, n minus 2, all the way down to 1. So it's kind of weird that Quicksort, even though it's fast for almost all cases, if you give it the already sorted array, it chokes badly and gives you an n squared algorithm. It's kind of weird. Okay. So that was our Quicksort runtime analysis. In the best case, if we get lucky, we get n log n behavior. The problem always splits cleanly into 2. Technically, if you want it to be really precise and pedantic, you could be really careful and be like, well, technically the pivot doesn't count, but it's okay. We didn't bother with that. We got n log n anyway, and it turned out to be okay. So hopefully the argument was good enough for you. And in the worst case, we saw the runtime was n squared, because every time, instead of splitting the problem into 2 equally sized subproblems, we actually ended up only decreasing the size of the problem by 1 every single time. So that's kind of weird. That Quicksort actually has different best and worst case behaviors compared to something like merge sort, which no matter what numbers you feed into merge sort, you will always get n log n asymptotic runtime. You can feed in the sorted array, you can feed in any array you want, random array, merge sort is always n log n. So if Quicksort has this weird case where it chokes on arrays that are already sorted, how can it be the fastest sort in real life? Well, it turns out that for almost all arrays in the world, Quicksort is n log n expected runtime. So that's what we'll be showing next. But before that, thoughts on the worst and best case? Yeah. Yeah, there was a question of, what if I just check if it's sorted first? That's a good point. We're going to solve the n squared case soon, but stay tuned, because it's something I want to get rid of, but not yet. OK, for now, we'll live with it, and we'll keep going. So the first thing I want to argue to you is that if I give you a random array, so it doesn't have to be the sorted array, there's any old random array, with extremely high probability, like the probability that I have an evil twin, that kind of probability will never happen. It's going to be n log n expected. So to actually prove it, I have to pull out some math and do an integral I'm not going to do that. I will just show you two intuitive arguments that I hope convince you that quicksort is n log n expected with extremely high probability, like astronomical probability. Okay, so here's my first argument, which is, well, maybe we're not super lucky, and every time the problem ends up in exactly, or the pivot ends up exactly in the middle. Maybe we're also not super unlucky in that it always ends up exactly as the first element, and we have the n squared case. But let's say we are pretty unlucky. Like we're very, very unlucky. Not the worst case, but like we're very unlucky in the sense that every time we choose the pivot, it's always pretty close to either edge. And by pretty close, I mean, let's say that there's always 10% of items on one side of the pivot and 90% of items on the other side of the pivot. If this was a random array, how often would this happen? Like approximately 10% of the time, you would get this unlucky case where you have these two very imbalanced arrays. One side has 10% of the items, one side has 90% of the items. So the probability that one side is 10% of the array or smaller is 10%. It's like picking a number between 1 and 10 at random and getting 1. You'd have to be pretty unlucky to get the 1. So that's the argument we're going to go with. So let's say this happens every single time. Like every time you choose the number between 1 and 10 at random, you get 1. You get super unlucky. So if we get super unlucky, let's see what happens on my array. Let's say n, we can use n if you wanted to. I'll just shove in 100 if it makes the math a little bit nicer, but you can do this with n as well. Let's say I have 100 items, and I'm very unlucky with my pivot. So roughly speaking, just give me an estimate. How many items are to the left of this pivot? How many items are to the right of this pivot? If I am unlucky and my pivot ends up close to the edge. Well, based on this 10% argument, I have approximately 10 items to the left of the pivot. That's approximately 10%, and 90% of items to the right side. This is pretty imbalanced, right? The most balanced case would be two equal size subproblems, and that'll be fastest. But I've gotten pretty unlucky here. I have a smaller problem and a much larger problem. Well, I got to solve them both. So let's go and solve them. One of them has 10 items. One of them has 90 items. So what happens when I solve the easier problem, the one with 10 items? Let's say I choose the left item as the pivot, and I get unlucky again. I roll the 1 on my dice or whatever. Well, in that case, I would get another problem that's 10% of the size, and another subproblem that's 90% of the size of this subproblem. So if it's got 10 items, what are the sizes of the two subproblems that pop out? If I get unlucky, well, one of them is going to be 1 item, and one of them is going to be 9 items, right? That's what we're saying when we get unlucky. We have 10% of items on one side, 90% on the other. If my input subproblem was of size 10, I'd get 1 item on one side and 9 items on the other side. Another imbalanced case. I really wish the problems were equal size, but they're not because I'm getting unlucky. What about this right side? Let's say I choose a pivot, and instead of landing in the middle, I get unlucky again. 3 times in a row. What are the chances? And this time, again, I have one problem that's 10% of the size, one problem that's 90% of the size. So, okay, I guess to pull up the left side first. Remember, there was 1 item, 9 items. Good. Now on this right side, how many items were there? There were 90 items. And if 10% fall on one side and 90% fall on the other side, what's 10% of 90? Well, that's 9. What's 90% of 90? That's 81. See, I can do the math. And so now I have 4 subproblems. They're pretty uneven. Look, I have one that's 81 items, and I have one that's just 1 item. So as I do this more, I'm getting all these lopsided arrays, and I have to solve all of them. But if I keep going down, eventually, even the largest subproblem, this one right here, this will cut by 90%, and then by another 90%, then by another 90%, all the way down until it reaches a size 1 array. So I'll get there. It'll just take more levels. Are we okay with at least the picture so far? It's kind of a weird picture to look at. Basically, the idea is instead of landing in the middle, I always land toward one side. And every time I split the problems, they're uneven, but in a way such that 90% of items are on one side, 1% of or 10% of items are on the other side. Okay, good. So how much work is done at every level? Let's do asymptotic runtime on this analysis now. So we know that every time we split, the array gets smaller, but how much smaller exactly? And how much smaller are the subproblems? Well, at the top level, I still have to do n work because I have to partition this whole array. Here, well, I still have to do n work because I have a smaller array to partition and a larger array to partition. but in total, the amount of work is still n. Maybe the small one's faster, but the large one is slower. So if you add it all up, you're still going to end up partitioning approximately n items. And same thing at the next level. It's true you have 4 subproblems that are of different sizes, but if you added up the total amount of work done for each subproblem, you would still get n. And the same holds for every single level. So then the only problem we have to solve is how many levels are there? And this will tell us the runtime of Quicksort, not in the best or worst case, but in this specific case that I'm painting. So how many levels are there? Well, at the first level, I had 100 items, and then the largest remaining subproblem was 90% of that size. So it had 90 items. There were more subproblems, but they'll vanish quicker. Then I had a subproblem of size 81, and then there are some other smaller subproblems that will probably vanish quicker. Then what about the next level? There will be a subproblem that is 90% of 81, and then another subproblem that's 90% of that, and then 90% of that, and then 90% of that. So the question is, how many times do you have to take an array of size n and reduce it by 90%, 90%, 90% before you get to arrays of size 1? Well, it turns out that is still a logarithm. Mind blown. Because remember, the idea with the logarithm is it's the number of times you divide. We said by 2 earlier because we were thinking base 2, but you could also do it with other stranger numbers, like, for example, 10 over 9. That would be the equivalent of multiplying by 0.9, or taking the array and cutting it to 90% of its size every single time. So the number of times you have to cut an array down to 90% of its size before it reaches 1, it's still a log n asymptotic behavior. It just has a different base. So because the number of levels is still log n, my runtime for this pretty bad case algorithm is actually still n log n. So even if I get super unlucky and my pivot always lands up very skewed toward one side, I still get n log n behavior. It's going to be slower in real life, but asymptotically, it's still n log n. The only thing that changed is the base, because instead of the subproblems becoming size 50% each time, they were size 90% each time. And the number of times I have to multiply by 90% before I reach problems of size 1, it's still log n, just with a different base. What would people like to know on Zoom? There was questions about, do you count the black boxes and why is it O and not theta? I think both of those have the same answer, which is that if you want it to be really precise, are you really doing n work at this layer? Not really. You're doing n minus 1 work because the black partitioned item doesn't count. And at this layer, are you really doing n work? Not really. You're doing n minus 3 work because these don't count. So if you want it to be really precise, you could actually take those out and do a really careful analysis and then tighten this bound to theta. But I've decided just to be lazy for a lecture and give you a big O bound. But if you wanted to, I believe if you did the exact analysis, you get something like theta of n log n minus n or something, and the lower order term would drop away. That's a good question, though. Why use Quicksort if they're both n log n? Soon. Why is Quicksort faster? Soon. But for now, I just want to convince you that it's fast. And for random arrays, like most arrays in the world, you will not get the n squared behavior, even if you're super unlucky like this. Okay. So the punchline is, even if you're really unlucky, every time you pick a number between 1 and 10, you get the 1, you are still guaranteed n log n behavior. Here's the second argument. Now this is one of those ones where those other guys would not have done it justice, so I have to be here and show it to you. Turns out, Quicksort is actually the same thing as binary search tree sort. Oh, what's binary search tree sort? Well, imagine if I took all the items in this array, left to right, and I shoved them in a binary search tree. So I start at the left, I go to the right, and I put everything in a binary search tree. And this is just a regular old binary search tree. There's no balancing, there's no red and black links, nothing like that. I just take the items and I insert them into a binary search tree. And then once I insert things into a binary search tree, I can do an in-order traversal, and the result will be a sorted array. And if you're not convinced, go back and think about what the in-order traversal is. Remember, the in-order traversal says, visit all the things to my left, visit me, and then visit all the things to my right. That will give you a sorted array if you do it recursively. But the idea behind BST sort is take all the items, put them in a binary search tree, and traverse it in the right order to get the sorted array. So here's what it looks like if I take the 5 and I stick it in the binary search tree. Well, the binary search tree has 1 item. It's 5. Well, that wasn't very interesting. Now I take the next item, which is 3, and I put it in the binary search tree, and it shows up to the left of 5. Then I take the next item, which is 2, I put it in the binary search tree, and I start at the 5. It's less than 5, I go to the left. It's less than 3, I go to the left. That's a good place to put the 2. By the way, the binary search tree, there's no balance. I'm just putting them straight in there with no regard for any sort of balance. Then I insert the 1. So I start at the 5, left, left, left. I insert the 1. Then I insert the 7, it goes there. Then I insert the 8. Then I insert the 4. Where does the 4 go? Well, I start at the 5. It's less than 5. I go to the 3. It's greater than 3. Right there. What about the 6? Well, 6 is greater than 5, so I go here. 6 is less than 7, so I put it there. So once I have everything in my binary search tree, I can do an in-order traversal, and I will get 1, 2, 3, 4, 5, 6, 7, 8. That's binary search tree sort. So I showed you binary search tree sort. I showed you Quicksort. And the thing that is really weird, but is actually true, is that these two are actually the same sort. And what do I mean by the same sort? I mean that the series of comparisons that they make is actually the same. So if I think about like what actually characterizes a search, well, one way to characterize a search is to write down the complete sequence of comparisons that you make. So for example, if I was like selection sorting this, then I'd write down that I compare 5 to everybody else. And then I compare, the 3 to everybody else, and so forth, or whatever. So I could write down the sequence of comparisons that I make. And it turns out that if you write down the sequence of comparisons that Quicksort makes, and you write down the sequence of comparisons that binary search tree sort makes, you get the exact sequence of comparisons. At a very deep level, Quicksort and BST sort are thinking about the exact same things. So here's what I mean. And honestly, this is one of those ones where if you just write out the full sequence of comparisons, I think it's easier to see. But I'll just show a rough picture for now. So let's say I want to partition on the 5. What are all of the items that had to get compared to 5 to finish the partition? I want to partition on 5. I have to compare everybody against 5 so that all the items less than 5 show up to the left, all the items greater than 5 show up to the right. So in other words, every item had to get compared to 5. Now switch to BST sort. In BST sort, how many items had to get compared to 5? All of them, because 5 is the root. So to insert anything into the tree, remember how we were like inserting, I want to find out where 6 goes? Well, I started at the 5 and I thought 6 is greater than 5. That was the comparison that I made. So BST sort checked 6 versus 5 to figure out where 6 goes, and Quicksort checked 6 versus 5 to partition on 5. So both of them had that same comparison. It turns out they have the exact same set of comparisons. So that's the initial value, which is 5. Everybody gets compared to 5, whether you're using Quicksort or BST sort. Now we have two smaller subproblems. What are all of the items that get compared to 3? Well, it's these items, 2, 1, and 4. Now look at the BST version. What are all of the items that get compared to 3? 2, 1, and 4. All of the items below 3, these are the items where I stopped at 3 and I asked, is the item greater than 3? Then go to my right, or is it less than 3? Go to my left. So in the same way that here I had to compare 2, 1, and 4 to partition on 3, in the binary search tree picture, I had to compare 2, 1, and 4 to 3 to figure out should I turn left or should I turn right after visiting 3. All these other items did not get compared to 3 because they're in different parts of the tree. And same in Quicksort, they're in different parts or different partitions, so I don't have to check these items against 3. Same thing on the right side. So here I have 7, 8, and 6 are the items that got compared against 7. And if you do this all the way down to the base level, you will see that Quicksort and BST sort actually end up doing the same types of comparisons, or rather the exact same sequence of comparisons. So they end up being the exact same sort. If you implemented them, the amount of comparisons you do is exactly the same. Whereas if you did, say, Quicksort and merge sort, the amount of comparisons is not guaranteed to be the same. It's kind of cool, kind of mind-bending. OK, that's the key idea. So everyone got compared to 5. Everyone to the left of 5 got, or everyone less than 5 got compared to 3, which is exactly what we see here. Everyone greater than 5 got compared to 7, which is what we see here. And so if you remember all the way back when that other guy showed you that if you have a random binary search tree, it takes n log n time to insert items into a random binary search tree. Well, for the same proof or with the same reason, quicksorting is also n log n time on average, because it's the same as inserting things into a random binary search tree, and that's also n log n time. because on average, a random binary search tree is balanced. By the way, I also think this is a pretty cool way to see the n log n and the n squared runtimes, because what would be the worst case in binary search tree sort is you get the really spindly tree, and it turns out building the spindly tree would take n squared time. So that's another way to see the n log n, bushy trees, n squared, spindly trees. It's such weird, deep connection that those other guys would have totally screwed up. But luckily you have me here, and we showed you BST sort versus Quicksort. Okay, thoughts, questions? Are we somewhat convinced that Quicksort by proof is n log n with very high probability? Here's, by the way, an experiment. So if you actually ran an experiment, I took a bunch of random arrays, and I sorted them, and I counted how many operations, how many compares did it take me to sort the arrays. I can actually plot them. So for example, this is telling me that a lot of arrays took around 12,000 compares to solve. And then the height of this bar tells me how many compares, or how many arrays out of all the arrays that I tried took 12,100 compares or whatever. So what we see if we plot all of the arrays that I tried and the number of compares they took is that most arrays took approximately 11,000 to 13,000 compares to do. And by the way, here I'm assuming that the array has 1,000 items, so n equals 1,000. And if you compute n log n, turns out n log n is around 12,000. So 1,000 times the log of 1,000 is approximately 12,000. And so you see that most arrays follow the n log n expected runtime. They all take around 12,000 compares. A very small number of them, let's say you get really unlucky, you might have taken 16,000 compares, or maybe 15,000 compares. So there are a few arrays that kind of went out here in the tail. Where's the n squared case on this picture? What is n squared? It's 1,000,000. Is it even on this picture? Nope. Is it like here? Nope. Is all the way, it's like in the other building, it's so far, because n squared is so far away from all of these cases. So imagine if you had a distribution roughly looking like this, and you wanted to land a point like 1 mile that way. Like good luck landing a point n equals 1,000,000, or rather the runtime being 1,000,000. It's not going to happen if your array is random. Okay, so that's another way to see it. Lots of arrays take 12,000, some take 15,000, but even that's not n squared. 15,000 is not 1,000 squared. If you wanted 1,000 squared, you'd have to go all the way off the slide. It's not happening. Okay, that was our runtime analysis. In the best case, n log n. In the worst case, n squared on average, or rather, if you have a randomly chosen array, n log n with extremely high probability. That is, probability that you'll get a point all the way that way. By the way, why do we use quicksort instead of merge sort? This is one of those questions where even I, with all of my vision, could not tell you the answer. It turns out in real life, if you just ran some experiments, quick sorting an array and merge sorting the same array, for some reason, quicksort just does better. And it has really, you'd have to go really deep down and think about how computers work and caching and all of these other things that we haven't seen in this class to really, truly see why it's faster. But for this class, we can say that even though they are asymptotically the same runtime, turns out if you do some experiments, you will find out that quicksort generally performs better. But I don't know if I have a one-sentence reason to convince you of that fact. You just have to trust that I know more than that other guy, or that quicksort is in the name. It's the faster one. You can run some experiments if you're not convinced. So now we have finished at least seeing what quicksort is, which is the key operation is partition, and with very high probability, it's n log n time. Thoughts, questions before I tell you about how to avoid that n squared you were also afraid of? Okay. So while it's true that if I had a random array, I would get n log n runtime, I still don't like this n squared. It scares me. In particular, what is the array that gives you the n squared runtime? It's the already sorted array. That's kind of scary because sometimes you might have an array that's already sorted and you call quicksort on it and it chokes and it crashes your program because n squared is too slow and the autograder times out. But we don't want that. So how do we avoid the n squared runtime? Well, turns out there's actually some different strategies for doing that. So we already saw that if the pivot always lands somewhere good, you get n log n runtime. And by good, we meant, for example, 10% from each edge. Even that could be good. Even 1% from each edge would be good. But In very rare cases, you do get n squared, and in real life, you can imagine you get n squared if the array is already sorted, almost sorted, or if the array has all duplicates. Try that one at home. You'll also get n squared. So how do you avoid worst case behavior? Kind of an open question. There's lots of different things you can try. So one thing that someone said earlier was, why not just pay n at the beginning to check if the array is already sorted, and if it is, switch to merge sort, or just don't do anything that's already sorted. That's not a bad idea. Anyone else have good ideas for how to avoid, or bad ideas for how to avoid the n squared case? How do you avoid the case where you end up in the n squared case? Yeah. Yeah, I think this is kind of similar to what the other guy said, which is a good idea, which is just check ahead of time, like do some analysis beforehand. And if it's a bad array, then switch, something like that. Anything else? I'll give you a couple if you don't have any. Yeah, one more. Shuffle it. I like that. So what if you just take the array, shuffle it around? Now it's random. Random arrays are n log n with high probability. So I like that too. So here's a bunch of ideas that we have. Shuffling, we have that one. Scan through and just check if it's already sorted, and don't sort if it's already sorted, or if it looks like it's going to be bad, and avoid sorting or use a different sort. Another one that none of you came up with, but still good. I mean, maybe you could if you had more time. But you could also go through the array and pick a better pivot. So far, we've just been lazy and we said, just pick the leftmost item. But what if you went through and actually picked a better pivot? What if you picked the best pivot every single time? Well, then maybe you can avoid the worst case. So here are some ideas. Let's go through some of them. OK. Here's Tony Ho writing Josh an email. I don't know what happened, but you can read it. OK. Let's talk about avoiding worst case quicksort. OK. So we already saw what quicksort is. I won't go through it again. Here are some 4 philosophies that we talked about. One of them is embrace randomness. Just pick a random pivot or shuffle before sorting. And we know that with very high probability, if your array is random, you're getting n log n runtime. You can try and be smarter with the pivot selection. Don't just pick the leftmost pivot. Pick one that you think will actually split the array into 2 roughly equally sized subproblems. You can use introspection. This is the one you all mentioned, which is if or I guess you all mentioned pre-processing, which is check the array beforehand and switch if quicksort is slow. Maybe a related approach that you kind of got close to was if the recursion goes too deep, like it's taking forever, just time out and call it quits and switch to a different sort, because you might be in an n squared case. So if the number of compares exceeds like 16,000, just switch to merge sort and call it quits. All of those approaches are valid. Let's explore them. So the first one is randomness. We already saw that if you shuffle the array ahead of time, now you have a random array, and we already saw that random arrays have n log n runtime with extremely high probability. So you can either pick the pivots randomly, so instead of always choosing the leftmost pivot, pick any old item in the middle and make that the pivot, or just shuffle the entire array before you sort. So that's what you could do, and if you do that, you are like this guy. That's a photo of me, on my motorcycle. I actually don't know who this is, but it's like some renegade, and he's like out there, being wild and free. So that's what randomness is. You're wild and you're free. Thoughts? Question? Yeah, the question was, is it inefficient because you're shuffling something that's already sorted? That is true that some of your arrays that are slow might have already been close to sorted, but asymptotically, you'll always get n log n runtime. So the main thing we care about here is we're avoiding n squared. If you think asymptotically, n squared is the one that's going to crash your program. So yes, it might take like 1 second longer or like a millisecond longer, but at least it won't crash your program, which is mainly what we care about here. That's a good point, though. Somehow it feels kind of weird that if the array is sorted, you're actually making it worse before you make it better. But at least you've avoided the n squared case that crashes your program, because that's the worst case. It's a good point, though. OK, here's the second approach, which is be smarter with your pivots. Oh, I'm almost out of time. Be smarter with your pivots. So here we could say, what if instead of choosing the leftmost item, you choose a better item? For example, choose the median, the exact middle item. Then you're guaranteed to get 2 subproblems of equal size. You could also do things that are a little bit more clever. So for example, let's say I had this array, ignore the green number. Let's say I have this array, and I don't want to scan through the whole thing to find the median, because that seems like a lot of work. What if I just check the first 3 items, 7, 2, and 3, and I don't look at the rest of the array, which could be huge? If I just check 7, 2, and 3, who's the best pivot? That's the last question before you all go. 7, 2, and 3, who's the best pivot? I like 3 because it's the middle of the 3 items. So one thing you can do is just check a couple of items, do a bit of sampling, and pick a pivot that you think is nice. It turns out if you do that, there's actually an adversary. You can pass in bad arrays, but I guess I'll continue that thought next time. So you can do exact median quicksort. You can also approximate the median, but if you do that, you're running into a little bit of danger. Then we talked about introspection, which is if the array or the sort is taking too long, just switch. While this is perfectly reasonable, you came up with it. Most people in practice don't do it. Okay, I was gonna depart you today in a blaze of glory, but I'll come back next time and I'll finish quicksort. So have a good rest of your Monday and come back next time. We'll do more quicksort. All right, see you.